all participants. We are going to start a second session, and this will be on cryptographic primitives involved in Bitcoins. Many cryptographic primitives or cryptographic protocols that is basically used in Bitcoins, and it will be delivered by Professor Ashish Chaudhary.
Okay, thank you. So we had seen in the morning session hash functions, digital signatures, some of their interesting properties. And recall that our goal is to design a cryptocurrency where we want fully decentralized system. We want anonymity, and at the same time, we would like to avoid double spending or allow a bad person to double spend a currency. So we will start with a very simple cryptocurrency, which I call as a goofy coin. And this is not a full-fledged system because this will be a centralized system. Because here a lot of trust will be put on a entity which I call as goofy. So here is how the goofy coin will operate. So the person goofy, who is a trusted entity, is a trusted entity in the sense we are assuming that he will behave honestly. So he will run the key generation algorithm, and it will obtain a verification key and a signing key for himself, and he will make his public key available for everyone. And we are not assuming here an anonymous system. So here we assume that everyone knows that this public key belongs to an entity called goofy. Now, what are the rules of this currency? Rule number one, only goofy can mint new coins or print currency. And here is how a create coin transaction will look like. So this is a create coin transaction. Okay, so it will have a command called create coin, and goofy only can execute this command. And along with producing a new coin, it will also assign a serial number. So everything is under the control of goofy. Goofy will have the serial number of all the coins that it has generated till now. And if it is now generating a new coin, it will assign a unique ID different from all the previous IDs. And he will also sign this transaction, okay, using his signing key. That's important. Now, once he generates this transaction and signs, and if he makes this transaction available in the public domain, then anyone can verify whether this is valid or not, right? So it is like saying the following. If I give you a piece of currency, a currency note, a 10 rupee note, how do you check whether it is a valid currency or not? You will look for the signature of the RBI governor. That's the basic check you will do. If the signature is not there, you will say that's a fake currency. Okay. The same way, what I'm saying here is that goofy will generate a new coin, sign it, and assign a unique serial number to the newly generated coin. Okay. And assuming that the signing key of goofy is available only with goofy, no one can generate fake goofy coins. Right. So that's rule number one. Rule number two for this goofy currency, goofy coin, is the following. Coins can be transferred. And the way coins are transferred from one entity to another entity is as follows. So imagine goofy has generated this coin. The number of the coin is, say, EA0910. And suppose it wants to give this coin to a person called Alice, whose public key is PK Alice and signing key is SK Alice. So for transferring this coin to Alice, what goofy can do is the following. He can create a new type of transaction, which I call as a pay transaction. Right. And this is different from a create coin transaction, right? So create coin transaction is used for minting new coin. Pay transaction is used or generated for transferring coin from one entity to another entity. So this pay transaction is generated by goofy because right now he's the owner of the coin. So he only can sign this transaction. And he's trying to give this money, namely the coin with serial number EA0910, to the bank account of Alice. And what's the bank account of Alice? The bank account of the Alice is PK Alice. Now, which coin he is transferring to Alice? For that, he will be stitching together the coin that is getting consumed and the coin which is getting transferred. So the coin which is getting consumed is the coin number EA0910, and that will be referred in this transaction. So here we have a hash pointer. Okay, so the paid transaction is actually referring to a coin which has been generated in the previous transaction. And that previous transaction is the create coin transaction. So that's how Goofy can transfer the money that he has generated to a new entity called Alice. And now, once Alice sees this transaction, she can verify whether this transaction is a valid transaction or not. So how she can verify whether this is a valid transaction? She can check whether this transaction is signed by Goofy or not. That she can do because the public key of Goofy is available in the public domain. So she can verify whether this transaction is properly signed or not. And then she will follow the hash pointer and trace the currency that is getting consumed in this transaction. So this is the consumed coin. So Alice has to verify whether indeed this coin exists or not with an entity who is signing this transaction. So this transaction is getting signed by Goofy. So you can imagine that this transaction, this pay to Alice, is nothing but a check issued by Goofy to Alice. The check is issued by Goofy because he is the owner of the coin and he is giving a reference to the coin which is transferring to Alice. That's how coins can be transferred. Imagine Alice has already got this coin. So this coin was generated by Goofy and then it got transferred to Alice. And now suppose Alice wants to transfer this coin to another entity called Bob, whose account number Alice knows. Then it's Alice's turn now to issue a check or execute a pay transaction. And now you can see that this transaction will be signed by Alice because she is right now the owner of the money. And she will be specifying to whom she is actually planning to transfer this money. And she will refer to the money that she is consuming. So she is actually trying to spend the coin with serial number EA0910, which has been generated or not generated, which has been transferred to Alice in this transaction. So she will be referring Bob to this coin. That, okay, here is the transaction in which I got a money transferred from someone else. So now Bob can verify whether indeed this transaction or indeed the check issued by Alice to Bob is a valid check or not. So what are the checks he has to do? So he has to verify whether the signatures of this check, of this check, of this check are valid or not. And these are the checks or transactions signed by different entities. So the Bob has to first verify whether this transaction is properly signed by Alice or not, because it is Alice who is transferring the money to Bob. And then he will follow the hash pointer and go to the transaction where the coin which Alice is now trying to spend to Bob got transferred to Alice. That transaction was signed by another entity called Goofy. So and to verify whether this transaction is properly signed by Goofy or not, Bob has to verify the signature of Goofy. And now he has to further follow this transaction to the transaction where this coin was generated. And if all this sequence of transactions are properly signed and everything gets verified, Bob will be convinced that this check is a valid check and he will accept it. And now after this, if again Bob wants to transfer this coin EA0910 to another entity, say Charlie, he will issue now a check signed by Bob. And he will refer to this transaction where the coin that he is now trying to spend to Charlie got generated for Bob. So that's how the coins can be transferred. Right, so very simple currency. We have a trusted entity who only can mint coins, and so that means the create coin transaction can be executed only by Goofy, but anyone who owns a coin can transfer it to another entity by executing a paying transaction, by creating a pay transaction. So even though this is a nice, this looks like a good cryptocurrency, it has some problems in the sense, first problem is that it is centralized. You have to put a lot of trust on Goofy. Okay. In the sense that it's only Goofy who can create new currencies. What if Goofy stops minting new coins? Or what if Goofy assigns or issues coins with same serial number to multiple entities? How do they verify whether Goofy is cheating or not? So in that sense, it's not a decentralized system. The second problem is that it does not prevent double spending. That means it is quite possible for a bad entity who owns a coin to spend the same coin at multiple locations or with multiple merchants. So let's see how it can be done. So imagine Alice, she is the owner of a coin. She is the owner of the coin number EA0910. And suppose she spends the coin to Bob by issuing the check to Bob. Okay. So Bob, when he sees this check, he will follow this route and he will check that, okay, everything is signed properly and it can trace back all the way to the origin of this coin. So for Bob, everything looks fine, but nothing prevents Alice to become malice, that means to get corrupt and issue the same check to Charlie. Okay, another entity called Charlie. So here is another transaction signed by Alice only. And now what she's trying to do is she's trying to spend the same coin which Goofy transferred to Alice to Charlie as well, which ideally should not be happen or should not allowed, because Alice has already spent that coin EA0910 to Bob. If she has already spent that coin 0910 to Bob, how can she again spend the same coin to Charlie? But when Charlie is verifying this check, he won't be aware that the coin 0910 has been already given to Bob and Bob has consumed it, because he is not able to see this transaction. The transaction is only from Alice to Bob. And now Alice to Charlie transaction, Bob is unable to see. So they are unable to raise a dispute. So that's why the Goofy coin with this serial number got spent at multiple locations. And in fact, Malice can keep on doing the same attack here. She can create another transaction and spend the same currency with serial number 0910 with a third merchant and so on, right? So what we will do now is we will enhance our scheme, Goofy coin, to another coin which I call as a Scrooge coin. This also will be a centralized system, because here everything will be controlled by a single central entity which I call Scrooge. But now we will increase the involvement of Scrooge. Earlier, Goofy's involvement was only to mint coins and distribute it to the users of the system. But now the participation of the Scrooge will be more here in this new system. So again, here Scrooge will be making available his verification key in the public domain. So his verification key will be available in the public domain. But apart from that, the Scrooge will maintain a blockchain, which will consist of all the transactions which has happened in this system called Scrooge coin. And only when a transaction gets included in the blockchain maintained by Scrooge, that transaction will be considered as a legitimate transaction. If that transaction is not included in the blockchain maintained by Scrooge, we will say that that transaction is an invalid transaction. So now you can see that why the role of Scrooge is getting more here, because he has to maintain a blockchain and he has to clear each and every transaction which is happening in the system, which was not the case in the previous currency, namely Goofy coin. So what will be the structure of this blockchain? So it will be a sequence of blocks, okay? And each block will have ID, which are distinct IDs. And the blocks will be linked together through hash pointers. And the head node or the head hash pointer of this blockchain will be signed by Scrooge. So Scrooge, you can imagine as the RBI governor here. And everyone will be keeping an up-to-date copy of this blockchain. Okay. And as I said, a transaction is considered as valid and executed only if it is recorded in the ledger of Scrooge. So now you can see that how the double spending attack can be taken care, which was happening in the Goofy coin. Because now if Malice tries to spend the same coin with multiple merchants, only one of those transactions will be endorsed by Scrooge, because we are assuming that Scrooge is a trusted entity. So if he receives or if he sees a transaction where Alice has already spent a coin with Bob, and then again if he sees another transaction where Alice is trying to spend the same coin to another entity called Charlie, Scrooge won't be including the second transaction in the ledger, and hence it will be discarded. So let's see some more details here. So there will be two types of transactions again. One will be kind of create coin, where new coins are minted and distributed by Scrooge. And another kind of transaction will be the pay transaction. The create coin transaction will be similar to Goofy coin. But now for simplicity, what we will do is the following. We will create multiple coins, and all those multiple coins which are generated by Scrooge are tied together and kept in a single block. This is just for the sake of efficiency, so that we can put together multiple transactions in a single block. Because if we are just recording a single transaction in a single block, then that will be enormous wastage of resources. So imagine we already had 72 blocks created in Scrooge's blockchain, and now say Scrooge is creating 73rd page of the blockchain. So what he can do is the following. If he is creating a create coin type of transaction, then he will be creating a new page, which you can call as new block, whose type will be create coin. And there will be multiple transactions of type create coin in this page. So you can index them by index number 0, index number 1, index number 2, and so on. Each such transaction will have a denomination. What's the denomination of the transaction, or what's the denomination of the coin that Scrooge has created? And the third entry will be the recipient address, namely the public key of the recipients to whom these coins are getting transferred to. And now what we can do is we can refer to different coins created in this transaction in the same way as we refer to various elements in an array. So in an array, we call the 0th element, first element, second element, and so on. So in the same way, if you have multiple coin create transactions in this block, to refer to a specific entity, we can use the array indexing. And of course, this transaction will be signed, this block will be signed by Scrooge, and only Scrooge can make public such blocks. So by default, such transactions will be considered as valid if Scrooge authorizes such blocks by signing it. Okay, so that's the first type of transaction for minting coins. And the second type of blocks will consist of pay coin transactions. That means suppose multiple entities are trying to transfer multiple coins to multiple entities. All such transactions or checks will come for clearing to Scrooge. What Scrooge will do is the following. Depending upon how many such transactions can be incorporated in a single block, he will collect those many number of transactions. He will verify each of those transactions, and after verifying them, he will include in his ledger and declare everyone that, okay, these are the transactions which are including in the next block of the blockchain. right? So the structure will be the following. So imagine this is the 73rd block created by Scrooge, whose type is paycoin. That means all the transactions in this block are of type paycoin. Now, in this particular example, there are 3 transactions of type paycoin in this block. The first transaction is trying to consume coin number 68,1. That means the coin which has been generated, whose record has been kept in 68 block and entry number 1. The second transaction is trying to consume coin which has been generated in the 56th page and entry number 2. And the third transaction is trying to consume the coin which has been generated in the 39th page, 0th entry. Of course, these coins will be available with different owners, right? It's not the case that all the 68,1, 56.2 and 39.0 are owned by the same entity, say Alice. It could be the case that 68.1 is owned by Alice, 56.2 is owned by Bob, and 39.0 is owned by Charlie. So they are the creator of the checks, and their signatures will be present here. And who are the recipients of the coin 68.1, 56.2, 39.0? They will be available here. Right. So what Scrooge will do is, once he get the check number 68.1 for clearance, 56.2 for clearance, 39.0 for clearance, he will verify whether those checks or whether those coins are indeed available for getting consumed or not. That means whether they have been already spent or not. If they are not spent, and if indeed they are owned by the persons whose signatures are available here, he will endorse those transactions and include them in this block. Right. So these are the rules according to which these transactions will be included by Scrooge. So Scrooge will check whether the consumed coins are created in the previous transaction or not. Consumed coins are double spent or not. Some of the consumed coins and created coins are same. What do I mean by that? So it might be the case that the consumed coin is of, say, value ₹5 and owned by Alice. And now suppose she wants to pay ₹2 to Bob. Right? So how do we handle with such a situation in the real world? If I want to pay ₹2 to Bob, then Bob should return me back ₹3 in exchange, right? That's the way we can handle this. So the way we handle it in cryptocurrency is the following. So this ₹5 coin will be now split into 2 coins. So Alice has to now create 2 transactions, one pay transaction to Bob and another pay transaction to self. And she has to give both these checks for clearance to Scrooge. Scrooge will check whether the sum of this ₹2 and this ₹3 is equal to total ₹5 coin which Alice is trying to consume, whether Alice has signed this ₹2 transaction or not, this ₹3 transaction or not, and then he will have to include both these transactions in this pay coin block. Okay, so that's how the pay coin transactions are created. And how the ledger gets updated. So you can imagine that after each round, so your round could be as long as, say, 5 minutes, 10 minutes, or 1 week, 1 day, depends upon the rules of the system. So you can imagine that after each round, Scrooge collects a set of transactions, approves them, and depending upon its type, it appends it in the ledger that he has, and he updates the head of the ledger that he's maintaining, and then he publicly announces it to everyone that, okay, here is the updated block or the new block which I want to include in the ledger. Okay. So depending upon the type of block that he's creating, the parties will verify the blocks as follows. So if it is a create coin type block, right, So what I'm saying here is the following. Pictorially, you can imagine the following. So this is the existing ledger, and everyone has the up-to-date head hash pointer. Now imagine that the 73rd block which Scrooge has created is of type create coin. Right? So these are the coins which he has created. He has signed it. So now he is willing to include this block as the 73rd block in the blockchain. So what he will do is he will publicly announce that, okay, this is the 73rd block I am going to add. And now everyone will do the following. They will verify whether indeed Scrooge has signed this head hash pointer or not, and whether this hash pointer is pointing to a block which Scrooge has made public. If both this verification passes, then everyone includes this 73rd block in their local copy of the ledger. So you can imagine that apart from Scrooge, every entity in the system is also maintaining a ledger. So as and when Scrooge is announcing new blocks, every entity goes and update their respective copies of the ledger. So if the 73rd block is of type coins created, everyone just verify whether the Scrooge signature is present or not, and whether the head hash pointer here refers to the new block which has been created. If both this verification passes, then all these coins, newly created coins, are endorsed and they will be accepted in the system. Okay, so forget about the role of the hash pointers here. That's not important here. So that's one type of block created by Scrooge and announced. Whereas if the type of block which Scrooge is making public is of type pay coin, right? So let's see how exactly the update happens in that scenario. So imagine at the moment, in the public ledger, there are 72 blocks, which has the record of all the transactions, all the created coin, all the valid transactions which has taken place, and so on. Now, suppose Alice is there who wants to pay the coin number 2,1. That means she is actually referring to the transaction number 1 in block 2, where a coin was generated for Alice, which she now wants to pay to Bob. So she will prepare a check or a transaction signed by Alice, and the recipient is Bob, and the coin that she is referring to, or that she is interested to pay to, that she is interested to consume, she is giving a hash pointer for that. So what she will do is she will give this check both to Scrooge as well as to Bob. Earlier in the Goofy coin, if she wants to pay a currency, a coin to some entity, she has to directly give that coin to the recipient. But now in the new system, she has to give the coin which she wants to pay both to the recipient as well as to Scrooge, because Scrooge has to endorse, because only when he endorsed that, okay, Alice is authorized to consume this coin 2,1 and pay to Bob, Bob will accept that transaction. So imagine Scrooge approves this transaction. For approving this transaction, Scrooge will check whether the signature of Alice is proper or not, and whether indeed Alice is the owner of coin number 2,1. Coin number 2,1 means the coin which has been, whether Alice is the recipient of the coin in the transaction 2,1 or not. The transaction in 2,1 could be either of type create coin or pay. That means it could be the case that Alice got this coin 2,1 directly from Scrooge, or it could be the case that this coin 2,1 got transferred to Alice from someone. Irrespective of the case, Alice will be the recipient of this coin. So Scrooge has to check that. So if this coin is indeed still available for spending, and if Alice is the owner of this coin, Scrooge will approve it. And imagine that he includes this transaction along with other transactions in a block number 73, which he is now making public, along with the updated head hash pointer. So if he makes this public, Bob will check the following. Bob will check whether indeed the new block has been signed by Scrooge or not. And he will go and check whether the transaction which Alice gave to Bob has been authorized by Scrooge or not. That means whether it is present in the block which Scrooge has newly inserted in the blockchain. If Bob checks that, okay, both the checks passes, he will accept this check. And now he is the recipient of the coin which Alice got in transaction number 2,1. Okay, so that's how double spending attack can be prevented in this Scrooge coin, which was the problem in the Goofy coin, because in Goofy coin, no one was getting their transactions endorsed by Scrooge. So even though we have now a working cryptocurrency, there are lots of problems involved with Scrooge coin. So let us try to understand what are the problems that are associated with this Scrooge coin. So the problem is that it is not decentralized. Why it is not decentralized? Because here everything is handled by this trusted entity called Scrooge, because he has to mint new coins and he only has to approve each and every transactions. There are lots of problems if Scrooge gets corrupted in the system. So for instance, what if he stops minting new coins? What he starts demanding transaction fees for validating transactions, right? So even if he mint coins, he won't accept or he won't endorse the pay transactions until and unless you give him a transaction fee. Suppose it becomes selfish like that, then again the entire system will get stuck. Or he can forge transactions on the behalf of honest parties as well. That means he can distribute multiple coins with the same numbers, or even if there are double spending attempts, he can simply endorse it and include in a new block and make it available in the public domain. So there are lots of problems with this Scrooge coin. So what we have to do now is we have to retain this blueprint of Scrooge coin, where the system will still more or less work in the same way. You will have two types of transactions: create coin transaction, pay transaction. Any coin which you are trying to pay should consume a coin which has been generated in a previous transaction, which everyone should be able to verify. So everything should be working in the same way as it was happening in Scrooge coin. The only thing is that whatever role Scrooge was performing, it should be decentralized. That means instead of putting a trust on a single entity, the trust should be placed on all the entities of the system. And only when collectively everyone approves transactions, then only a transaction should be approved. And then we get all the effect, all the benefits of Scrooge coin. And the way we can do the decentralization actually leads us to the Bitcoin cryptocurrency. So let me pause for a couple of minutes here and see if there are any questions from the audience. Are there any questions? Okay, so there are no questions, then let's resume. So as I said, there are lots of problems in Scrooge coin. We have to decentralize the rule of Scrooge. And when I say decentralize the rule of Scrooge, we have to get answers to the following question. If there is no centralized Scrooge in the system, then who should maintain the ledger of the transaction? Who should have the authority to validate new transactions? Who should mint new coins? Who should determine how the rules of the system change? And how do Bitcoins acquire the exchange value? So these are the questions that we now have to answer if we want to decentralize the role of Scrooge. So the answer to the first three questions, namely who should maintain the ledger, who should have the authority to validate transactions, who should mint new coins, The answers to these questions are actually the technical aspects of Bitcoin protocol, and this is what we are going to discuss next. Okay, the answer to the last two questions, they are not the technical aspects of the Bitcoin protocol. So to understand how exactly the decentralization happens in the Scrooge coin cryptocurrency, we have to look into a related problem, which we call as distributed consensus or Byzantine agreement problem in distributed computing. This is a fundamental problem in distributed computing. So what's the problem setting here? We have a set of mutually distrusting parties, say n number of parties, and they are mutually distrusting. That means they are not in talking terms with each other. They do not trust each other, right? And they are not willing to let their respective data made available to others. And since we are talking about mutually distrusting parties, to model the distrust in the system, we assume that we have a centralized entity, which I call as adversary, denoted by A, who can control a subset of these n parties. Okay. Now, which parties are going to be controlled by the adversary will not be known beforehand, and possibly it may not be known even at the end as well. We only will be knowing that during the execution of a protocol, out of the n parties, some of them could go wrong. Some of them start colluding and may behave in any arbitrary manner as dictated by this entity called adversary. But who exactly are the entities who are behaving maliciously or who are not following the instructions, we may not be knowing beforehand. Each party or each entity here has some private input, xi. It could be as small as a bit, or it could be as long as a file. It could be as large as a huge database file. Okay. So we abstract out the input of every party by xi. And the goal is to run a protocol according to which the parties exchange messages with each other, so that at the end of the protocol, the parties who are not under the control of the adversary, which we call as honest parties, they have a common output. That's why the name agreement. That means even though parties may start with different inputs, our goal is to ensure that at the end of the protocol, they should have agreement on the output, right? Now, that agreed output X must be the input of some honest party. That's the important thing here, which we call as the validity property. Because if the end goal of the parties is to just agree upon a common output, then everyone can just say that, okay, we all agree on 0. That's all. That does not make the problem interesting. To make the problem interesting, we also demand here that, okay, even though we want the output of all the honest parties to be same, say X, that X should be the input of some honest node. If this property is achieved, we call this validity. So our goal is to design a protocol according to which the parties exchange messages, and finally they agree upon a common output, and that common output should be the input of some honest party. Okay. So if you are wondering that why exactly we are interested in this consensus or Byzantine agreement problem here in the context of Bitcoin, so since we want to decentralize the role of Scrooge, our goal will be to now design a consensus mechanism which allows the parties to agree upon the next block in the blockchain so that they can update their local copy of the blockchain. And after each round, we need to run a consensus protocol which allows the parties to decide which transaction or which set of transactions we should go and put next in the blockchain. Okay, so what I'm trying to say is the following. If there is no Scrooge available in the system who is going to endorse your transactions, and we want to decentralize the role of Scrooge, then we will encounter the following situation. Say Carol wants to pay some coin to Dick. Tom wants to spend some coin to Charles. Alice wants to pay some coin to Bob, and so on. And they announce these transactions in the network. Okay. If they announce these transactions in the network, then every entity will receive these transactions in different order, and they will be locally verifying these transactions with respect to their local copy of the blockchain. But then after that, they have to agree or decide that what should be the set of transactions which should be endorsed by the entire system and put as the next block in the blockchain. So you can see that now we will be requiring a consensus protocol. Why consensus protocol? Because each entity will have its own set of transactions which it has approved. The set of transactions which I might have received and decided to approve might be different from the set of transactions which my peer neighbor might have received and decided to approve, and so on. So I cannot put simply my block in the blockchain, because the transactions which are there in my copy of the node which I am trying to insert in the blockchain may not be the same as my peer neighbor, and so on. So that's why we now need a consensus mechanism which allows the parties round after round to decide what are the set of transactions which should go and occupy as the next block in the global ledger. Okay, so what I am saying here is the following. Each node will maintain a list of outstanding transactions. So suppose this system has received these 3 transactions. This system has received these transactions. This system has received this transaction, and so on. And locally, this party has prepared a block where these are the transactions which it wants to put in the block. Similarly, this system wants to put this set of transactions in the block. This system wants to put this set of transactions in the block. Now, with these blocks as the input to the consensus protocol, the parties participate. And after the end of the consensus protocol, they will agree upon a block which everyone should go and put at the end of the local copy of their ledger. And that's how everyone can maintain a unified copy of the global ledger across multiple systems. So even though this might look like a very simple thing to implement, in the context of Bitcoin network, we cannot run the classical consensus protocol. So even though consensus or Byzantine agreement is a well-studied problem in the context of distributed computing, there are several consensus protocols available in the literature. Unfortunately, we cannot deploy them as it is in the context of Bitcoins. This is because now we might have malicious participants in the system who may try to unnecessarily include unauthorized transactions in the blockchain. And more importantly, your Bitcoin network is a peer-to-peer network, which is dynamic, where you can leave the system, join the system as and when you want. Whereas the classical consensus protocols are designed assuming that the set of participants who want to run the protocol are static. No one is allowed to leave the system or join the system in between. Right from beginning till end, the set of participants remain the same. But in the context of Bitcoin network, a user can join anytime, a user can leave anytime. So you cannot run the classical consensus protocol in the context of Bitcoin network. And more importantly, the reason we cannot run the consensus protocols in the context of blockchain or Bitcoin is the following. The classical consensus protocol assumes that we have a set of n parties whose identities are known to each other. Okay. Whereas in the context of Bitcoins, the identity of the system, identity of the participants are not known. The identities here are nothing but public keys, that's all. Due to this, a bad guy can launch what we call a Sybil attack. What do I mean by Sybil attack? So since the entities here are the public keys, what an adversary can do is it can run the key generation algorithm multiple times. And as a result, it will be now producing multiple public keys, all of them under the control of the adversary. Honest participants will never do that. Honest participant will have only one account number for themselves, or actually the number of account number they have indeed belong to them. But what a civil attack means here, an adversary can create fake accounts on his behalf. And now the challenge is basically to run a consensus protocol in the absence of the identities of the parties and in the presence of the civil attack. Okay. So that's why we cannot run the classical consensus protocols in the context of blockchain, because in the classical consensus protocol, we assume that we have n participants and say up to t corrupt, up to t of them are corrupt. But a civil attack means even though there is only one corruption here, we can create multiple fake public key numbers which can be treated as multiple entities controlled by the adversary. So classical consensus protocol do not take care of the civil attack. So it might look like that if we want to decentralize the role of Scrooge, we are kind of getting stuck because we don't have any consensus mechanism. And if we don't have any consensus mechanism, how exactly we can hope to extend the blockchain and include new transactions, because parties have to agree that what should be the next set of transactions to be included in the blockchain. So they need to reach agreement. So for the moment, assume that we have an intelligent node selection algorithm, a random node selection algorithm to be more specific. And my assumption here is that this node selection algorithm is smart enough in the sense that in every round, it will choose one of the available public keys uniformly at random. That means out of all the entities who are available in the system, it will select one of them uniformly at random. And if there is an adversary who has actually created multiple fake public keys, even on behalf of all those public keys, the chances of getting selected the chance of adversary getting selected is at most once. That means it should not. So more specifically, in this particular example, say adversary has created 1, 2, 3, 6 public keys. And apart from the adversary, we have 6 good guys. So actually, logically speaking, we have 7 entities in the system, 6 good guys plus 1 bad guy. But in terms of public keys, we have 12 public keys, but we do not have actually 12 different public keys. We have 7 public keys. What I am assuming here is that my node selection algorithm is such that the chance of getting any of these 6 entities getting selected in the next round or adversary getting selected in the next round is 1/7. That means even adversary's chance of getting selected in the next round as a selected node does not increase proportionately to the number of fake public keys that it has created. So assume for the moment I have such a random node selection algorithm. So if I have such a random node selection algorithm, here is how the decentralized Scrooge currency will operate, or this you can imagine as the Bitcoin consensus protocol. This is a simplified version. I am hiding many technical aspects here. So this will be an everlasting algorithm because the ledger or the log of the transaction will keep on getting populated forever. Okay, because new and new transaction will keep on happening. So what we do, if you have some transactions, that means you want to pay money to someone, you broadcast those transactions. Then each party, what it does is the following. It prepares a candidate block by collecting the new transactions. So that means if I am a participant of the system, and if I listen to multiple transactions which people want me to kind of approve or authorize, then I will individually verify whether those transactions are valid or not. I will be maintaining a set of outstanding transactions. I will be maintaining a pool of transactions. That means I myself am playing the role of Scrooge, and every entity in the system is playing the role of the Scrooge. So I will be having a huge list of pending transactions which I have received over the network. Now, after every time clock, I will be clearing my set of pending transactions by picking a set of transactions from my pending list, verifying them, approving them, and I prepare my candidate block. And then the parties run the node selection algorithm. That means who should be selected to propose the next block in the blockchain. Okay. Then everyone will be agreeing upon that, okay, that particular node is now getting selected. So let's wait for his candidate block to be broadcasted. So the candidate who is getting selected by this node selection algorithm, his goal will be now to broadcast the candidate block that he has created. So he also has played the role of Scrooge. He has his own list of outstanding transactions. He might have created a candidate block, which he will now broadcast because now he is being selected. And once I receive a candidate block broadcasted by the selected candidate, I cannot blindly include it in the local copy of my blockchain, because if the candidate who is selected is a corrupt node, he might be trying to unnecessarily include unauthorized transactions in his candidate block. So I have to verify whether this candidate block is valid or not. That means I will myself now check whether those transactions, that means the transactions which he has included in his candidate block, are double spending attempt or not, signatures are present or not, whether the coins which have been consumed are spent legitimately or not. So whatever checks I am supposed to do as per the role of Scrooge coin, I will do myself on the proposed transactions proposed by the selected candidate. And if all of them passes the test, I will include it in my local copy of the blockchain. And then again, I go to the next iteration. That means all the transactions which have been now included in my local copy of the blockchain, they will be flushed from my set of outstanding transactions. That means those checks are not cleared. And now in the next round, I will be again repeating this process. So pictorially, here is how the consensus mechanism works. So you can imagine that this is the list of outstanding transactions for this entity. This is the list of outstanding transactions for this entity. This is the list of outstanding transactions for this entity. I stress here that the list of outstanding transactions might be different for different entity, because transactions are broadcasted in the network, which is a highly imperfect network. They may reach to different entities for clearance in different orders. So it's not the case that the order in which I receive a set of pending transactions will be same across my peers and so on. And imagine that this is the up-to-date copy of the local copies of the blockchain. That means 2 blocks have been already added, and they are common across all the entities of the Bitcoin system. Now it's the turn for 3rd block. So depending upon which set of transactions this entity decides to clear, it will include or it will prepare his candidate block. Similarly, this entity will prepare his candidate block. This entity will prepare his candidate block, but they cannot directly include it in the blockchain. That's why right now it's in the dotted form. Now we will run the node selection algorithm. And suppose this node is getting selected to propose the next block. So he will announce his candidate block. Once he broadcasts his candidate block by making it available in the network, the receiving entities will verify whether this candidate block is genuine or not. If it is genuine, then they will include it. That's why these dotted arrows are now converted into full arrows here. And now this process will be repeated. That means the transactions which have been included in this block will be now flushed from the list of outstanding transactions here, flushed from this set of outstanding transactions here, flushed from this set of outstanding transactions here. And now the next block will be added depending upon who gets selected and so on. That's how the ledger now gets updated after every iteration. So now let's stop here and do some analysis whether what are the properties that this simplified blockchain consensus protocol achieves. So let's first try to understand whether someone can steal someone else's coin or not. So that means if I am a user and I do not give my signing key to anyone else, can someone create a transaction on my behalf and transfer the coins that I own to someone else? Right? That means imagine I am Bob. I have 20 BTC, 20 Bitcoin available with me, which I might have got in some transaction. Alice knows the details of those transactions. But now Alice wants to spend this 20 Bitcoin to herself without my consent. For that, Alice has to create a transaction where she would like to pay the 20 Bitcoins owned by Bob or me to herself. So she is putting herself as the recipient of this check. But then she has to put Bob's signature in this transaction. Then only someone can approve this transaction, because if the coins which are trying to be getting spent here belongs to Bob, then Bob's signature should be present in this transaction. And assuming that signatures cannot be forged, adversary or a bad Alice simply cannot steal my coin. So this is not possible. Okay. So that achieves one basic property. No one can transfer money from my account to her account without my approval. So you can imagine that the signing key is kind of acting as my net banking password. In the absence of my net banking password, no one else can log into my account and transfer money. Okay. Let's see a denial of service attack. Is it possible that an adversary prevents an honest party's transaction forever? That means even though I want to pay someone some money, my transaction never gets approved by anyone. Will I encounter such a situation? That will be a denial of service attack. So again, imagine I am a genuine user. I have 20 Bitcoins to spend. And I create a transaction that, okay, I want to pay someone this 20 Bitcoin. I announce this transaction. So I announce this transaction. So this transaction will go to both Malice as well as to Bob. Both of them will include my transaction in their respective outstanding list of transaction. Okay, so you can imagine that my check went for clearing both to Alice as well as to Bob. Imagine that Alice got selected to propose the next block in the blockchain. And suppose she simply pretends that she never got my check for clearance. In that case, Alice won't be including my check in the next block, which she is proposing. She might give preference to other checks because those are the parties who are paying commission to Alice to give preference to their checks. Fine. So my check didn't got selected in this iteration. But suppose in the next iteration, Bob got selected and Bob is honest. And if Bob is honest, my check will be definitely present in his outstanding list of pending transactions, and he will include my transaction in the next block, and my transaction will got approved. So that's why, assuming that the chance of any node getting selected in the random node selection algorithm is equal probable, even though a bad node selector can refuse to give preference to my transaction, I will never face a denial of service attack scenario. So this is also not possible. Now let's see whether double spending is possible in this consensus protocol or not. Okay, so imagine that Alice has paid Bob some coin. Okay, so Alice has created, so this coin CA, this is owned by Alice. And she has created a transaction, signing a transaction, and she has paid this transaction. Through this transaction, she has paid this coin already to Bob. And suppose some honest node has been selected during the node selection algorithm, he has cleared this check. The check transferring the coin CA to Bob. That means this check has been endorsed and this is now available in the blockchain. Now, what Alice can do is she can again try to spend the same coin CA to someone else, say to herself, which she should not be allowed to do because she has already spent the coin to Bob. That coin CA is no longer available with Alice. It's now in the possession of Bob. But what Alice can do is she can create a fake public key for herself, different from her original public key, because remember, everyone can open any number of bank account. And she can now create a fake check, not fake check, invalid check, I would rather say, invalid transaction, signing and saying that transfer this coin CA, which belongs to me, to this account number A prime. Now, why this transaction is invalid? This transaction is invalid because the coin that she's trying to pay, namely CA, is no longer in the possession of Alice. It has now been transferred to Bob. So ideally, this transaction is an invalid transaction. But suppose what happens is the following. The next iteration, the node which gets selected for proposing the next block in the ledger is a bad node, corrupt node. That means that node is now a friend of Alice. And even though he knows that this is an invalid transaction, because he knows that this coin CA has been already transferred to Bob and it has been recorded in the ledger, still that corrupt node includes this transaction in the candidate block that he has proposed. Now, if such a situation happens, then in the terminology of Bitcoin, we say that a fork has happened. Why a fork has happened? Because up to this point, everything was fine. But here now we have two different branches coming out. In one branch, we have a transaction where coin CA got transferred to Bob has been approved. Whereas in another branch, we have a transaction that the same coin being transferred from CA to A prime is getting approved. And now we don't know what to do, whether to treat this as a valid block or whether to treat this as a valid block. We don't know. Okay, because both branches are valid. Because it might so happen that the person who has proposed this block was unaware that there is another person who is also trying to prepare this block. And it may so happen that immediately after the person who has proposed this block, immediately in the next iteration, this block is announced by a corrupt node. And at that point,
सर आपका थोड़ा वॉइस वो लैग हो रहा है, एक बार माइक को म्यूट करके वापस अनम्यूट करके फिर एक बार स्टार्ट कर लीजिए। मैं थोड़ा सा वॉइस लैग हो रहा है, वॉइस में थोड़ी डिस्टॉर्शन आ रही है।
ओके, एक मिनट में माइक फिर बंद ही कर देता हूँ।
हाँ नहीं, माइक को एक बार स्टार्ट वापस कर लीजिए, बस वो स्टार्ट सही हो जाएगा। पीछे भी हुआ था ना एक बार, पिछले सेशन में हुआ था थोड़ा सा।
हेलो।
हाँ सर,
ठीक है अभी?
हाँ सर, परफेक्ट नाउ।
Okay, okay, right. So in the terminology of Bitcoin, we call this scenario as a fork. And now from the viewpoint of the Bob does not know that whether he is now the owner of this coin CA or not. Because one node says that this coin has been transferred to him. another node says that this coin is now getting transferred to A prime. So this is now a double spending attempt. Now, whether this double spending attempt is successful or not depends upon what will be the next block in the blockchain. That means whether it is this branch which gets extended or whether it is this branch which gets extended. Depending upon which of the two branches get extended, that will determine whether the coin CA belongs to Bob or not. Okay, so that's why the strategy of the Bitcoin is the following. Bob, ideally, when he sees that the coin CA being getting transferred to Bob is included in this blockchain, should feel confident that, okay, indeed, this transaction is now approved. But he should not immediately believe this transaction. The strategy of the Bitcoin network is the following. The strategy is that honest parties always extend the current longest branch. That means if they see a scenario where there is a fork happening in the system, they should give preference to the branch which is of bigger length and try to extend that. And in this particular case, both the branches are of the same length. So now we are in a dilemma whether the honest parties should produce or should extend this branch or whether they should go and extend this branch, right? Because in this particular case, both the branches are of same length. So that's why to prevent a double spending attack, Bitcoin resort to what we call as K confirmation rule. And what is this K confirmation rule? The K confirmation rule says that an entity should not immediately believe a transaction to be approved until and unless it gets K confirmations. And what do I mean by K confirmation? By that, I mean that there should be K blocks on top of the block where that transaction got approved. Only when there are K number of blocks on top of the block where the transaction got approved, the transaction should be taken as confirmed. And in this particular case, when this transaction where the coin CA got transferred to Bob is included, where it is currently not included but just available with Bob, it will be treated as a zero confirmation because right now the coin is available, this transaction is available only with Bob. But when this transaction CA getting transferred to Bob is included in the blockchain by one of the honest nodes who is getting selected during the node selection algorithm. If this is happening, then we will say one confirmation. After that, if there is another node who actually extends on top of this block, we will say that this transaction got two confirmation. On top of that, if there is another node who has proposed the next block on top of this block, we will say that this transaction got three confirmations and so on. So the idea here is that as more and more confirmations are happening, that means as more and more nodes prepare their next candidate block on top of the block where this transaction has been approved, the chances are that on a long-term basis, this transaction will be considered as affirmed. It won't be overwritten. Okay. Because the only way it can be overwritten is the following. If it so happens that once it got, say, 3 confirmation, and after that in the next 4 iterations, it's only the bad nodes who get selected for extending the blocks. And suppose what they do is they try to produce blocks on top of this double spend transaction, then only this branch will go longer and this branch, the above branch, will get shorter. But for that, what should happen is the following. There should be several malicious nodes which should be selected in close succession, and they should be able to produce the next false blocks on top of the double spend transactions. But this is unlikely to happen if we assume that majority of the participants in the Bitcoin network are honest. That's what I mean by honest majority. So if I assume that 51% of the people are good in the system. That means the chance that in every iteration a bad node gets selected as the nodes as to propose the next block, then the chances for the probability that a bad node gets selected is 1/2. So assuming that I already got K confirmations for this transaction approving coin CA being transferred to Bob. Now, if I want to kind of undo this, it should happen that for the next K iterations, it should be consecutively K bad nodes who are selected to propose the next node, and they should propose something on top of this incorrect block. But the probability that for next K consecutive iterations, I get K bad nodes to propose the next sequence of K blocks is 1/2 power K, which is a very small quantity. So that prevents this double spending attack. So if you are wondering what exactly is the value of K for the Bitcoin protocol, the K is equal to 6. That means until and unless Bob gets 6 confirmations on top of this block, he cannot take this transaction to be a valid transaction. Only when there are 6 confirmations on top of this block, he can take or he can consider this transaction to be approved. And then the chances that this transaction is kind of undone in a future iterations is 1/2 power 6, which is a small quantity, relatively a small quantity, right? So now everything boils down to how exactly we do the random node selection, right? So remember, I am assuming here that in each iteration, we will be able to intelligently select one node who should be able to propose the next block in the blockchain. That node selection algorithm should be totally random, and it should be secure against Sybil attack, and with probability 1/2, it should pick an honest node as the next node in each iteration, right? So the question is how exactly we get such an intelligent node selection algorithm, given that we do not know the identity of the users in the system, because the identity of the users are hidden here. We only know the public keys, and there could be multiple public keys controlled by a single entity. So the way we design this node selection algorithm is actually linked to the question how new coins are generated in the system, because we have not yet answered the question that how in the decentralized Scrooge system new coins are getting minted. So it turns out that we have 2 questions here: how new coins are generated in the system, and how the next node or the node for proposing the next block in the blockchain is decided. It turns out that we can couple both these questions in a very clever and intelligent way. Basically, we create a situation where even the bad nodes, potentially bad nodes, are rewarded for honest behavior. And if we kind of create a scenario, a situation where bad nodes are rewarded for honest behavior, then that automatically deters even a potentially bad guy to behave honestly during this random node selection, right? That means it forces a bad guy to behave like a good guy. Okay. So here is how we do the incentive mechanism in the context of Bitcoin by doing what we call as block reward. So if you are actually planning to extend the blockchain, you want to approve a set of transactions, collect them, propose a block, and make it available in the blockchain network, we associate a processing fee which will be given to you. And how do you claim that processing fee? So if you are the user who is selected to propose the next block in the blockchain, then what you do is, apart from the other transactions which you have prepared in your candidate block, you include a special transaction saying that I am paying myself this much coin as a processing fee. Okay. And if you are indeed getting selected, and if indeed your block gets included in the blockchain, then everyone will agree to the fact that you have earned a reward for proposing the next block in the blockchain. And the current block reward is 25 Bitcoin, but after every 4 years, it is half, which is approximately after every 210,000 blocks, the reward gets halved. Okay, and that's the only way to mint new coins in the Bitcoin system. That means there is no trusted entity who will be generating new coins in the system. If you want to generate new coins in the system, the only way is that you kind of collect a set of transactions for approval and hope that you get selected for proposing the next block in the blockchain. And if indeed you get selected, you pay yourself a reward which everyone will accept. Now, if you are wondering that why this block reward is kind of acting as an incentive for the bad nodes to behave like a good node, is because of the following. Suppose there are the good users in the system whose strategy will be always to extend the longest branch whenever they see a fork. Because the Bitcoin rule is that if you see a fork in the system, you should give preference to the longest branch. Now, suppose there is a bad node who got selected to propose the next block in the system. Right? So if he got selected, then he will be getting a reward for himself. That reward is a significant amount of quantity, namely 25 Bitcoin. And if he indeed behaves honestly by increasing or by extending the longest branch in the system, his transaction will be considered as approved. Okay. And if on top of that, nodes which get selected in the next iteration, anyhow, they will be extending the longest branch. They extend the longest branch, then this transaction will be considered as approved, right? But if I go back and say that this node who got selected for proposing the next block do not behave honestly, so ideally he should have proposed something on top of this block, but suppose he decide to act smartly and try to extend a block which is shorter in length. That means he's trying to propose something on top of this block, which he should not do. And he awards himself a reward of 25 BTC. Okay, so now from the viewpoint of the users, there will be a fork in the system because now we have two branches here. And now suppose in the next sequence of iterations, it's only the honest nodes which get selected for proposing the next block. And suppose by chance the honest nodes start increasing or extending this branch. If they start extending this branch, then what will happen is the following. The transaction where A himself rewarded 25 BTC will be considered as a null transaction, invalid transaction. And as a result, the 25 BTC, which was supposed to be rewarded to this node selector, won't be given to the node selector, right? So that's why this incentive of rewarding yourself with 25 BTC or whatever is the block reward, and the strategy of always giving preference to the longest branch, both these two techniques ensure that double spending does not take place with high probability. Okay, so now what are the problems that we are left with to solve? We have to come up with this random node selection. That means how exactly we decide which node should propose the next block in the blockchain. And remember, it should be secure against Sybil attack. And we have to design a node selection algorithm which should prevent instability in the system. Instability in the sense, because if we leave everyone to become a node selector, if we allow everyone to select the next node, next block in the blockchain, then everyone may try to earn some Bitcoin by trying to propose the next block in the system. So that's why, to ensure that we take care of the Sybil attack and to ensure that we do not create instability in the system, we very nicely get the solution for the random node selection algorithm. And this is through another technique which we call as the proof of work, which in the Bitcoin jargon we also called as Bitcoin mining. Let me resume here. So what is this proof of work? So this is a very nice concept introduced by Cynthia DeWerck, Moni Now, and their seminal work in '92. Let's not go into the history of what exactly is proof of work, but let's see how exactly it is applied in the context of Bitcoin mining. Why I'm calling it mining? Because your goal is to be elected as the next block proposer for the blockchain, because if you are elected as the entity to propose the next block in the blockchain, then you will be rewarded 25 BTC, which is a significant amount. Okay, so you can imagine Bitcoin mining as the following. Each entity in the system has some resource. That resource could be anything. We will soon define what exactly is that resource. We want a mechanism where the chance of being selected to propose the next block in the blockchain should be proportional to how much resource you own. The resource in the context of Bitcoin is how much computing power you have or hashing power you have. There is another category of cryptocurrencies based on proof of stake, where the resource is how much money you own. Okay. So directly go to how exactly the proof of work is instantiated through hash puzzles in the context of blockchain. And let me quickly recall what exactly was hash puzzles. So an instance of hash puzzle consists of a random ID, a random binary string, and you will be given a target set Y. The solution for the hash puzzle will be a binary string X, such that when you hash the puzzle instance with this input X or solution X, the output belongs to this target set Y. So what is the hash puzzle used in the context of Bitcoin mining? So imagine I want to get elected to propose the next block in the blockchain. And I have this transaction pool. These are the set of transactions which I want to clear. Of course, one of these transactions will be the reward transaction, where I would be paying myself 25 BTC. Now, to propose the next block, or to get elected to propose the next block, what I have to do is the following. I have to find a nonce, which is a binary string, such that if I hash my candidate block, and my candidate block will have the set of transactions which I am approving, and a nonce, and a hash pointer of the previous block which I am trying to extend. All of them hashed together should give me an output which has n number of leading zeros, where n is some parameter. And that determines your target set Y. Right? Why it determines your target set Y? Because if I want my solution to be a 256-bit strings where the first n bits are 0, then it is equivalent to saying that basically I have to find out a nonce such that if I hash the nonce along with all the transactions in my candidate block plus the hash pointer of the previous block, then it should be less than the target value. And the target value will be as determined by the remaining 256 minus n bits. If I can find such a nonce, then basically I have solved the puzzle, and then I can consider myself to be elected for proposing the next block in the blockchain. So how exactly the random node selection works? So imagine there are multiple users in the system. Each of them has their own transaction pool. namely the set of transactions that they got for approval. Each user will be preparing his own candidate block that will determine the instance of the puzzle for the respective entities. So if this entity has included these 3 transactions in his candidate block, then that determines the puzzle instance for the entity number P1. If this is P2 and he has selected these transactions, then that determines the puzzle entity. And each of them is independently trying to find out a nonce, which can help him or her to find out an output which starts with n number of zeros. And the winner of the puzzle or the winner of the round will be whoever finds the nonce first and announce it. Okay, so there are a couple of properties which we want to be addressed through this hash puzzle. First thing, it should be difficult to compute. And let's see how exactly it is difficult to compute and how exactly we can control the difficulty level. So remember, we want the solution to be such that the hash output starts with n number of zeros. So if I want to increase the difficulty level of the problem, I just have to increase the value of n by 1. Because if I increase the value of n by 1, the target set gets reduced by half. That means if my n is equal to 0, my target set is the entire space of bit strings of length 256 bits. But if I set n equal to 1, that means I will accept a solution only if your hash outcome falls in this range. If I make n equal to 2, that means I will accept a solution only if your hash function follows in this range. So that means I can control the difficulty level of the puzzle by increasing the value of n. And I don't know what exactly is the current difficulty level, but 2 years back it was n equal to 60. Okay, so that means if I assume that hash functions behave like a random function, that means the outcome of each hash computation is giving me a random value. And if the output of the hash function is n bits long, if the output of the hash function is L bit strings, and if my difficulty level is n, then on an average, I need to compute these many hash values, or I have to try 2 to the power n number of nonce values in order to solve the puzzle. But computing 2 to the power n number of hash values will take enormous amount of resources. So I should have that much resources available with me in order that I get selected to propose the next node. Okay. The second important aspect of this hash puzzle is that if someone has actually won the puzzle and announced the result, it's very easy to verify that. Because for verifying the solution, you again don't need to solve the puzzle. So for instance, if suppose this user is able to solve the puzzle, that means he got the corresponding nonce, and I was trying to solve it, but before me he was able to come up with nonce, then I could verify whether indeed this nonce is a valid solution for the puzzle instance or not. Because I have to again recompute the hash value of this candidate block and check whether it starts with n number of zeros or not. Okay. And there is this third aspect of hash puzzle property, which I think I can skip because that's not very much important. So with that, more or less, I think I am done with my part, whatever I was supposed to cover. I would like to do some advertisement. So if you like my talk, today's talk, then I'm offering 2 courses on NPTEL. One is exclusively on cryptography. It is an introductory course covering all the foundations of modern cryptography. We cover encryption, decryption, and other than that, all other basic cryptographic primitives. I already offered this course earlier. You can find all the video lectures, transcripts at this link. And the same course I will be offering in January again. And I am offering a new course on discrete mathematics in January, which on discrete mathematics, it will cover all the fundamental topics in discrete mathematics.